There are some truly bizarre objects in our solar system, like Io with its endless volcanoes, Titan with lakes and seas made of liquid hydrocarbons, Pluto with nitrogen glaciers, the two-toned Iapetus, or Miranda, whose surface looks like a patchwork quilt. The list goes on. So compared to all that cosmic strangeness, our calm and gray moon might seem kind of boring, especially since it's always right in front of us. We've seen it hundreds, if not thousands of times. But here's the truth. The moon is anything but boring. Next time you look up at the night sky, ask yourself, doesn't it feel a little strange? A little different? Maybe there really is something off about it. And actually, there is. The moon is weird, it's unique, and it's raised more than a few questions. Today on Space Unraveled, we're diving into the moon's most unusual traits. This is the first episode in a new series where we'll explore fascinating astronomy topics and start building our own little community. So hit that subscribe button, tap the bell, and don't forget to drop a comment below. Tell us what you think about the video and what we could improve. Previously, John, have touched on the moon in different formats, and over time, I've gathered a bunch of ideas that don't need their own episodes, but together they make a great one. Today you'll find out, is it true that Earth and the moon are actually a double planet? Why is the moon so different from other moons? Why is it so massive? And are all its craters really the same depth? And much more. Our moon really is one of a kind. It's the only large moon orbiting a rocky planet in the solar system. Other planets either have tons of moons or none at all, but only Earth has a moon like this one. Sure, the moon isn't the largest satellite in the solar system. It ranks fifth. But let's look at the ones ahead of it. They all orbit gas giants, which are way bigger than Earth. So if we compare relative sizes, the moon looks like a giant. What makes the moon so unique is its proportions. Its radius is more than a quarter of Earth's. No other moon-to-planet ratio comes close. For example, the biggest moon in the solar system, Ganymede, is about 27 times smaller than Jupiter. Here's what Jupiter and Ganymede look like in scale, and here's Earth and the moon. Some scientists even refer to Earth and the moon as a double planet, and we'll come back to that. This size ratio raises a lot of questions. How did it happen? What's the explanation? As you might guess, it all ties back to the moon's origin story. And once again, it's a weird one. Its formation history is drastically different from that of most other moons. In the inner solar system, the rocky planet zone, moons are almost non-existent. Only Mars has two tiny, potato-shaped rocks, Deimos and Phobos, just 16 and 26 kilometers across. The moon? Almost 3,500 kilometers in diameter. Most known moons orbit gas giants, and how do they form? Pretty much the same way planets form around young stars. Some leftover material from the star turns into a protoplanetary disk, and in it, planets are born. The same happens with giant planets. A disk forms around them, and moons take shape. That's why most moons of gas giants orbit in the same plane as their planet's equator. A big clue to how they formed. Another type of moon is a captured one. These form somewhere else and get pulled in by a planet's gravity. Their orbits are often tilted, stretched out, with high eccentricity. Some can be tiny, others quite big. Neptune's largest moon, Triton, is believed to be a captured object. But our moon didn't form like that, not even close. There are some alternative theories. For example, that the moon was flung off from Earth during a rapid spin. But the leading model today is what's called the giant impact hypothesis. According to this model, the moon formed from debris that was ejected into orbit after a young Earth collided with another protoplanet, about the size of Mars. What's fascinating is that this formation method is totally different from how most other moons came to be. If we draw analogies, stars to planets, planets to moons, we usually see clear size differences. Planets are much smaller than stars, though of course there are exceptions, like TOI-5205b and TOI-3512b, giant planets orbiting tiny red dwarfs. But those are rare, and they break our models. So if a moon forms from a disk, like with gas giants, something as big as the moon shouldn't really exist. But with a collision, it becomes possible for two bodies to end up with the kind of mass and size we see in the Earth-Moon system. Even so, it's still not that simple. A recent study published in Nature Communications was titled, "Massive Planets Can't Form Proportionally Massive Moons." It tackled one of astronomy's big questions. Why haven't we found any confirmed moons around exoplanets, despite thousands of discovered planets? To investigate, researchers ran a bunch of computer simulations of protoplanet collisions. They focused on rocky and icy planets, skipping gas giants and mini-Neptunes. Turns out, not all collisions produce a partially vaporized disk, a key stage for forming a moon. Most simulations resulted in fully vaporized disks, which don't allow large moons to form. Why? Because those disks are gas-dominated. Any forming mini-moons, ranging from 100 meters to 100 kilometers, quickly lose momentum and fall back to the planet. Fully vaporized disks showed up most often in rocky planets over 6 Earth masses and icy ones over just 1 Earth mass. More massive bodies generate more energy during collisions, which completely vaporizes the debris. So if this is true, the best place to look for big moons is around rocky planets no heavier than 6 Earth masses. That's where conditions favor moon formation, which makes our moon even more special. The moon plays a huge role in keeping Earth's conditions stable. It helps maintain our axial tilt and affects the climate. I talked about this in a previous video on the factors needed for life. But even among rocky planets, and even assuming a giant impact, a moon this big is rare. The planet's mass, impact energy, and disk composition all have to line up just right. So let's go back to that earlier question. Could Earth and the moon really be a double planet? In 2003, the European Space Agency's website published an article titled, "Moon, Welcome to the Double Planet." It was released to mark the launch of the Smart 1 spacecraft. The article claimed that Earth and the moon aren't just a planet and a satellite, but a double planet. The main argument? Their unusually similar size ratio, which we've already discussed. Of course, that was a public outreach piece, not a peer-reviewed paper. But when something like that appears on a major space agency's website, it feels almost official. Even though the truth is more complicated, it all comes down to terminology. What counts as a planet? A moon? A double planet? These depend on definitions and agreements. The International Astronomical Union sets the standard. The latest official definition of a planet came in 2006. That's when Pluto lost its planet status. According to that definition, a planet must orbit the Sun, have enough mass to be roughly spherical, clear its orbital neighborhood. That last part is why Pluto got the boot. It turns out its orbit is packed with other objects of similar size, like if there were a bunch of other Marses near Mars's orbit. But even the other planets haven't fully cleared their neighborhoods. Earth has near-Earth asteroids, and Jupiter has Trojan asteroids. What exactly does cleared its orbit mean? That's still up for debate. The definition doesn't spell it out, and that's why it gets criticized. And that's just the first tricky term. What about double planet? What criteria do two bodies have to meet to qualify? The IAU hasn't defined this term. In fact, they haven't even officially defined planetary moon. So if we want to confidently say Earth and the moon are a double planet based on international standards, we can't. At least not yet. Still, there are some interesting unofficial arguments. One is based on mass. If two bodies orbit a star and also orbit each other, and their masses are similar, that's a double planet. But in practice, perfectly matched masses are rare. Even a 1% difference can get the smaller one labeled a moon. The moon's radius is about 27% of Earth's, but its mass is 81 times smaller than Earth's, so it's not close to a 1-to-1 ratio. Not by mass, anyway. But again, there's no official threshold. Another argument is based on the system's center of mass, the barycenter. It's the point both bodies orbit around. In binary stars, the barycenter is often outside both stars. That's considered normal. But when one body is much more massive, like the Sun-Earth system, the barycenter is inside the larger one. In our case, it's deep inside the Sun. By that logic, some say a true double planet should have a barycenter outside both bodies. That's the case for Pluto and Charon. Their mass ratio is just 10-to-1, and their barycenter is beyond Pluto's surface. Not so for Earth and the Moon. Earth's radius is about 6,370 kilometers, and the barycenter is just 4,650 kilometers from Earth's center, still within Earth. So by this metric, Earth-Moon doesn't qualify as a double planet. Pluto-Charon does. But here's the twist. Pluto isn't considered a planet anymore. So how can it be in a double planet system? Long story short, there's no official definition for double planet, no universal criteria, and by the informal ones, Earth and the Moon don't quite make the cut. But while researching, I found a fun twist. A paper suggesting we just call the Moon a planet, a real ninth planet in the solar system. Published in 2017 in the International Journal of Astronomy and Astrophysics, the paper claims that the Moon meets all 3 IAU criteria for planethood. We've covered them already. Orbit the Sun. Be roughly spherical. Clear its orbit. The Moon is clearly spherical. Clearing the orbit is trickier, but the paper argues that the Earth-Moon system has done so in its own way. The most controversial part? Does the Moon orbit the Sun? It looks like it orbits Earth, but when you plot its path in a sun-centered frame, it closely follows Earth's orbit. Earth barely tugs on it, they fly together. In simulators like Universe Sandbox, the Moon doesn't draw loops around Earth. It moves along with Earth in a near-identical orbit with slight wobbles. Couldn't that mean other moons, like Europa or Titan, are also planets? The authors say no. Those moons are more strongly bound to their planets than to the Sun. But the Sun pulls on the Moon almost twice as strongly as Earth does. That puts the Moon in a very weird place. So by this logic, the Moon orbits the Sun, has a round shape, and has a cleared orbital path, which means it fits the definition of a planet. It's an intriguing idea, but it hasn't caught on. Possibly because the journal it was published in, Scientific Research Publishing, has been flagged as a predatory publisher with questionable review practices. Still, it highlights one thing. The definition of a planet is far from settled and still needs work. And one last story, one that conspiracy theorists love to bring up, is the mystery of the Moon's craters. People have long wondered, why are all the Moon's craters round, even when the asteroids hit at angles? And now, another question. Why are all the craters supposedly the same depth? Here's an article online claiming the Moon only has a thin layer of dust, and underneath is something solid, maybe even artificial. Their argument? Supposedly, all craters are the same depth. That's simply not true. Crater depths vary. For example, Tycho crater is almost 5 kilometers deep. Small ones? Just a few dozen meters. But yes, and as craters get bigger, their depth doesn't grow proportionally. Large craters are relatively shallow. Take Tycho again. It's 85 kilometers wide, but its depth is only 1 to 18 of that. Big craters usually have a depth-to-diameter ratio between 1 to 15 and 1 to 25. They look more like shallow dishes, small ones, more like deep bowls. Why is that? High-speed impacts release immense energy. Rock behaves almost like a fluid. Computer models show the surface splashing, and the final shape forms after stabilization. Over time, lunar gravity smooths things out, preventing super deep craters. Otherwise, the Moon would be covered in gaping holes. Any body in hydrostatic equilibrium has physical limits for mountain heights and crater depths. That includes both Earth and the Moon. So no, Moon craters are not all the same depth. That claim comes from misunderstanding or oversimplification. But it's exactly these questions that push us to learn more and dig deeper. That's the beauty of curiosity. Even weird questions can lead to real discoveries. So what did you think of this episode? Support our new channel, Space Unraveled. Subscribe, hit the bell, and leave a comment. What did you enjoy? What should we improve? See you in the next one.